Hello everyone. Today's topic is science behind whiskey's maturation. The transformation of this fiery liquid into a smooth, multi-layered amber spirit isn't magic. It is an evolutionary process governed by organic chemistry and thermodynamics. Today, we are bypassing the romantic myths of maturation to track the exact chronological journey of how giant wood polymers break down, filter, and alter the physical chemistry of alcohol. Our journey begins before the whiskey even touches the barrel, during a process called pyrolysis, the thermal degradation of wood polymers using controlled fire. Oak is naturally constructed from three primary pillars: cellulose, hemicellulose, and lignin. First, look at cellulose. Making up nearly half of the wood's structural mass, it is a highly crystalline polymer composed of tightly packed glucose chains. Because of this rigid and soluble framework, cellulose survives the maturation process mostly intact, acting as the physical scaffolding of the barrel. Hemicellulose is a completely different story. Hemicellulose is an amorphous, highly branched polymer made of diverse sugar monomers. It is thermally unstable. When the cooper toasts the inside of the cask, these branched chains readily break apart. This thermal cracking yields volatile furfuryls and furanones, the molecular origin of the deep caramel colors, baking spices, and nutty sweetness that later leach into the liquid. Deep within the wood lies the ultimate flavor engine, lignin. Lignin is a massive three-dimensional aromatic polymer that gives trees their rigid woody strength. It is naturally packed with complex phenolic rings. When exposed to intense heat, this massive macromolecule undergoes depolymerization. The giant polymer chains crack open, releasing smaller, liquid-soluble monomeric phenols. The most prominent among these is vanillin. Over years of seasonal temperature shifts, the ethanol water solution acts as a powerful solvent, slowly pulling these free-floating vanillin molecules out of the degraded timber matrix. This is the precise material science behind those iconic layers of rich cream, vanilla, and smoke. But a whiskey cannot become elegant merely by taking flavors from the wood. It must also purge its own chemical flaws. This introduces the mechanics of subtractive reaction in whiskey. When a barrel is heavily charred, the extreme heat completely alters the surface chemistry of the wood, transforming the organic polymers into a layer of elemental carbon. On a microscopic scale, this char layer behaves exactly like an industrially engineered activated carbon filter. It becomes a network of dense micropores with an immense surface area, as temperature fluctuations force the liquid into and out of the barrel walls. This carbon matrix acts as a molecular sieve. It utilizes a physical process called adsorption, where gas and liquid molecules adhere to a solid surface. The heavy, unpleasantly pungent sulfur compounds from the new make spirit, such as dimethyl sulfide, which smells like boiled vegetation, are physically captured and locked away within the carbon pores. Over the first 24 months, this continuous filtration strips out the raw, vegetal flaws, purifying the spirit from the inside out. Simultaneously, the barrel operates as a semi-permeable membrane. Because the wood polymers are not completely hermetic, the cask breathes. Lower molecular weight aldehydes and volatile fractions slowly escape through the microgaps of the staves and evaporate into the atmosphere, a natural mass loss phenomenon widely known as the angel's share. The final phase of maturation happens entirely within the liquid solution, governed by oxidation, esterification, and thermodynamics. In a matured whiskey, water and ethanol do not form rigid or permanent cages. Instead, they remain a highly dynamic mixture where hydrogen bonds are constantly breaking and reforming trillions of times per second. However, ethanol is an amphiphilic molecule. It has a water-loving polar head and an oil-loving nonpolar tail. Because of this, ethanol molecules tend to naturally cluster together at the liquid-air interface, or the surface of the spirit. Over years of aging, two critical shifts completely alter how we perceive this solution. First, the cask isn't entirely airtight. Atmospheric oxygen slowly permeates through the micropores of the wood staves. This triggers slow, continuous oxidation, driving the conversion of alcohols into aldehydes and carboxylic acids. This oxidative pathway is crucial. It softens and breaks down any remaining harsh, pungent sulfur compounds, rounding out the spirit's sharp edges and noticeably mellowing the mouthfeel. Second, these newly formed carboxylic acids, like acetic acid, begin to react directly with the ethanol. This is the mechanism of esterification. Over time, this reaction synthesizes a complex array of esters. These volatile organic molecules are the primary chemical engines driving the rich, mature, fruity and floral aromas, like green apple, pear, and banana, that define a premium aged whiskey. At the same time, the spirit extracts large, dissolved wood compounds, specifically polyphenols and tannins. By dissolving into the ethanol water matrix, these macromolecules alter the physical properties of the liquid, including its surface tension and viscosity. They influence the activity coefficient of the mixture, essentially modulating how easily ethanol and other volatile aromatic molecules evaporate from the surface of the liquid into the air. This suppression of harsh volatility is why an aged whiskey tastes remarkably integrated, round, and smooth compared to raw distillate. This also explains the true science behind adding a drop of water to your glass. Adding water changes the polarity of the solvent. Because ethanol is less polar than water, a sudden increase in water drives the ethanol molecules, along with the hydrophobic aromatic esters trapped beside them, rapidly to the surface. It doesn't shatter a structure. Rather, it shifts the thermodynamic balance, causing a sudden release of volatile esters into the headspace of your glass. It is a rapid change in chemical volatility that opens up the whiskey's bouquet. What we call maturation is actually a masterclass in organic material science. It is a slow, multi-decade progression where raw spirit systematically dismantles a tree's structural polymers, transforms them into an aromatic treasure trove, uses a carbon matrix to filter its own flaws. The next time you hold a glass of finely aged whiskey up to the light, you aren't just holding a drink. You are looking at a beautifully balanced, highly dynamic solution of organic chemistry. Cheers!